Why does the universe only move in one direction when the fundamental laws of physics say it shouldn't? Atoms don't have clocks. Electrons don't remember what came before. And yet, somehow, you are aging, coffee is cooling, and stars are burning toward their deaths. We are tracing the mathematical bridge that connects the strange chaos of quantum entanglement to the forward march of time itself. And what we find suggests that the flow of time is not a fundamental constant of the universe. It may be something far stranger. It may be a byproduct of information quietly spreading, hiding. Picture a glass of water tipping over. The water spills, spreads across the floor, and soaks into the carpet. No one has ever seen the opposite happen. No one has ever watched water gather itself back into a glass and leap onto a table. And yet, if you looked at the individual water molecules bouncing and colliding on their way to the floor, every single collision obeys laws that work perfectly well backward. Run the film of two molecules colliding in reverse, and it looks like a completely legitimate physical event. Nothing about Newton's laws, and nothing about the deeper quantum equations underneath them, forbids the spill from reversing itself. And yet it never does. This is the paradox that has haunted physicists for more than a century, and it sits at the heart of one of the strangest unsolved questions in all of science. Why does time have a direction at all? Isaac Newton's laws of motion do not care which way the clock ticks. If you take any solution to Newton's equations and simply reverse the direction of time, you get another valid solution. A cannonball that is fired into the sky and falls back down looks equally correct running forward or backward. The same is true, even more deeply, in quantum mechanics. The Schrödinger equation, which governs how the wave function of a particle evolves, is time-symmetric. Mathematically, there is nothing that distinguishes the future from the past. A single, isolated particle does not know it is supposed to be moving toward some destined future. In principle, its evolution could just as easily run in reverse. This creates an unsettling contradiction. If the fundamental laws that govern every particle in your body are symmetric in time, why does your body only move in one direction? Toward wrinkles, toward memory loss, toward the eventual stopping of your heart. Why can a single particle move backward in time, at least on paper, while a trillion particles working together, like the water molecules in that spilled glass, apparently cannot? The answer that physicists have slowly assembled over the past 150 years begins with a concept most people associate with heat engines and steam trains, entropy. But by the time we reach the modern understanding, entropy will look almost nothing like the tired old idea of disorder that gets taught in a first-year science class. It will look like something closer to a river of information, draining out of view. Before we go further, it's worth pausing here, because what we are about to walk through connects some of the strangest results in modern physics. And if any of this makes you want to dig deeper on your own, this might be a good moment to save this video, because we are only just getting started. In the 19th century, the German physicist Rudolf Clausius introduced the word entropy to describe a strange, one-directional quantity in thermodynamics. He noticed that heat always flows from hot objects to cold ones, never the reverse, unless you do work to force it otherwise, the way a refrigerator does. Clausius proposed that there was a quantity, entropy, that could only increase or stay the same in any closed system. This became the second law of thermodynamics, one of the most battle-tested principles in all of science. Later, the Austrian physicist Ludwig Boltzmann, gave entropy a deeper, statistical meaning. Entropy, he argued, was simply a measure of how many different microscopic arrangements of particles correspond to the same macroscopic appearance. Think of a deck of cards. There is exactly one arrangement that counts as perfectly sorted, ace to king, by suit. But there are trillions upon trillions of arrangements that count as shuffled. If you shuffle a sorted deck, you are enormously more likely to end up with a shuffled-looking deck than to accidentally land back on the sorted one, simply because there are so many more ways to be shuffled than to be sorted. Boltzmann's insight was that entropy increasing is not really a law that forces disorder on the universe. It is simply the overwhelmingly more probable outcome, given how vastly more numerous the disordered arrangements are compared to the ordered ones. Boltzmann's colleague, the physicist Joseph Loschmidt, immediately spotted a problem with this reasoning, one that still carries his name today. If the underlying laws of mechanics are perfectly reversible, Loschmidt argued, then for every process that increases entropy, there must exist an equally valid mirror image process that decreases it, simply by reversing the velocity of every single particle involved. Nothing in Newton's equations forbids this. So why should entropy have any preferred direction at all, if the underlying mathematics is blind to the difference between forward and backward? This became known as Loschmidt's paradox, and it struck directly at the heart of Boltzmann's proposal. Boltzmann's eventual answer was subtle. He conceded that, yes, in principle, a spontaneous entropy-decreasing sequence of collisions is not mathematically forbidden. It is simply staggeringly improbable, buried among an almost incomprehensibly larger number of entropy-increasing possibilities. Reversing a system's velocities perfectly enough to unspill a glass of water is not impossible. It is simply so astronomically unlikely that no one should ever expect to witness it. Not in the lifetime of the universe, around the same period. The Scottish physicist James Clerk Maxwell devised a famous thought experiment to probe just how strange this statistical view of entropy really was. Imagine a tiny, intelligent being, later nicknamed Maxwell's demon, stationed at a small door between two chambers of gas. The demon watches individual molecules approach the door and, using perfect knowledge of each molecule's speed, opens the door only for fast molecules heading one way and slow molecules heading the other. Over time, without adding any energy in any conventional sense, the demon could sort a uniformly warm gas into one hot chamber and one cold chamber, seemingly decreasing entropy and violating the second law of thermodynamics outright. For nearly a century, this puzzle unsettled physicists until Rolf Landauer, and later Charles Bennett, showed that the demon is not actually cheating physics at all. The demon must store information about each molecule it observes, and eventually, that information has to be erased or reset to keep sorting new molecules. Landauer proved that erasing information is never thermodynamically free. It always costs a minimum amount of energy, released as heat into the environment, and that heat cost exactly balances whatever entropy the demon appeared to be removing from the gas. Maxwell's demon does not break the second law. It reveals that information and entropy were secretly the same currency all along. A discovery that would turn out to be one of the most important clues on the road toward understanding time's arrow through quantum entanglement. This statistical explanation was elegant, but it left a haunting question unresolved. If disorder is simply more probable than in principle, order could still spontaneously reappear, given enough time and enough chances. Boltzmann himself worried about this. he proposed the unsettling idea that maybe our entire observable universe is just an extraordinarily rare, temporary fluctuation of order arising randomly out of an otherwise maximally disordered cosmos, and that we exist now, in this brief and improbable pocket of low entropy, purely by chance. Most physicists today find this idea deeply unsatisfying, because it would predict that a smaller, simpler fluctuation, like a single conscious brain floating in space, should be enormously more common than an entire ordered universe full of galaxies, stars, and complex history. If Boltzmann's reasoning were the full story, we should expect to be nothing more than a momentary illusion. Since we are not, something is missing. The missing piece, physicists gradually realized, is not really about disorder at all. It is about information, and specifically, about who has access to it. This is where the story shifts from the language of steam and heat to something closer to the modern language of computation and quantum physics. Over the past several decades, and especially through breakthroughs across the 21st century, physicists have increasingly treated information itself as a physical commodity, something with real, measurable weight in the equations of nature, not just an abstract bookkeeping trick. The physicist Rolf Landauer showed in the 1960s that erasing a single bit of information always requires a minimum amount of energy to be released as heat. This was a profound clue. It meant that information was not just something we use to describe physics from the outside. Information is entangled, quite literally, with the physical laws themselves. To understand how this connects to entropy and the arrow of time, we need to talk about entanglement, arguably the strangest and most misunderstood phenomenon in all of quantum physics. When two quantum particles interact, something remarkable can happen. They can become entangled, meaning their properties become linked in a way that has no equivalent in classical physics. If you measure the spin of one entangled particle and find it pointing up, you instantly know the spin of its partner, even if that partner is on the other side of a galaxy. Albert Einstein famously distrusted this, calling it spooky action at a distance, because it seemed to violate his deep intuition that nothing should be able to influence anything else faster than the speed of light. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, Published, what became known as the EPR paradox, a thought experiment designed to argue that quantum mechanics, as it stood, must be an incomplete description of reality. They reasoned that, if measuring one particle could instantly tell you the state of a distant partner, then either an unsettling faster-than-light influence was occurring, or the particles must have carried some hidden, predetermined information all along. Information quantum mechanics simply failed to describe. For nearly 3 decades, this remained a philosophical disagreement, with no clear way to test which interpretation was correct. That changed in 1964, when the physicist John Stuart Bell devised a mathematical inequality that any theory based on hidden, predetermined information would have to satisfy. Quantum mechanics, Bell showed, predicted that entangled particles would violate this inequality. It was, for the first time, a genuinely testable difference between Einstein's intuition and the strange predictions of quantum theory. But decades of increasingly precise experiments, including the work that earned the 2022 Nobel Prize in Physics for Ailing Aspect, John Clauser and Anton Zeilinger, confirmed that entanglement is real, that Bell's inequality is indeed violated exactly as quantum mechanics predicts, and that entanglement does not actually allow information to travel faster than light. What it does allow is something even stranger. Two particles can share a single, unified quantum state even while being physically separated, with no classical hidden information needed to explain the correlation between them. Here is the crucial part. When two particles become entangled, each individual particle, considered on its own, loses something. Before entanglement, if you wanted to describe a single particle's quantum state, you could do so completely, with a clean, precise mathematical description. After entanglement, the particle no longer has its own independent, complete description. Its properties are only fully defined in relation to its entangled partner. If you try to describe the entangled particle by itself, ignoring its partner, you are forced to describe it using probabilities rather than certainties. Information that used to belong to the particle alone has effectively leaked outward, becoming shared, distributed, and in an important sense, hidden from any observer who only has access to that one particle. This is precisely where a mathematical tool called von Neumann entropy enters the story. Named after the brilliant Hungarian-American mathematician John von Neumann, who helped lay the mathematical foundations of quantum mechanics in the early 20th century. Classical entropy, the Boltzmann kind, measures how many microscopic arrangements are consistent with what we can observe. Von Neumann entropy measures something related but distinctly quantum. It measures how mixed, how uncertain the quantum state of a subsystem has become due to entanglement with something outside of it. If a particle is completely isolated and in what physicists call a pure state, its von Neumann entropy is zero. There is no missing information. But the moment that particle becomes entangled with another system, and you can only observe the particle by itself, its von Neumann entropy rises above zero. The more thoroughly entangled it becomes, the higher this entropy climbs, up to a theoretical maximum where the particle, viewed in isolation, looks completely random. Even though the combined system of particle plus partner remains, technically, perfectly well defined, it helps to picture this with a concrete example. Imagine two coins that have been quantum entangled so that they always land on opposite faces, one heads and one tails, no matter how far apart they travel before being flipped. If you only ever look at one coin by itself, its outcome appears perfectly random, 50% heads and 50% tails, carrying maximum von Neumann entropy from your limited point of view. But the moment you compare notes with whoever is holding the second coin, the randomness vanishes completely. The combined system of both coins together was never random at all. It was always a single, precisely defined arrangement. The entropy was never really about disorder in any deep sense. It was about the gap between what a limited, local observer can see and what the full, combined system actually contains. Physicists capture this gap with a related quantity called mutual information, which measures exactly how much of that seemingly missing information becomes recoverable once you are allowed to compare both parts of an entangled system together. As entanglement spreads across billions of particles in the real universe, that combined system needed to recover the missing information grows so large and so physically inaccessible that for any realistic observer, the information is effectively lost forever, even though, in the strictest mathematical sense, it was never destroyed at all. This distinction between information being destroyed and information merely becoming inaccessible turns out to be one of the most important ideas in this entire story, because quantum mechanics is built on a deep principle called unity, which insists that information can never truly be destroyed, only ever hidden, scrambled, and spread. This gives us an entirely new way to think about the growth of entropy in the universe. one that doesn't rely on vague notions of mechanisms or disorder at all. Entropy increases in this picture because quantum systems are constantly interacting with their surroundings, becoming entangled with more and more particles in the environment, the air molecules around you, the photons bouncing off your skin, the vibrating atoms in every surface you touch. Every one of these interactions spreads a little bit of information out of the system and into the wider environment, where it becomes, for all practical purposes, unrecoverable, not gone, not destroyed, just scattered so widely and entangled so thoroughly into so many other particles that no realistic observer could ever gather it all back together and reconstruct the original simple state. This process has a name in quantum physics. Decoherence is the mechanism by which the strange, fragile quantum behavior of superposition, where a particle can be in multiple states at once, gets washed out and hidden as that particle entangles with its environment. It is why we do not see large objects, like a coffee cup or a cat, existing in quantum superpositions in everyday life. The moment any quantum system interacts with a sufficiently large and complex environment, its quantumness becomes entangled away into billions of other particles almost instantly. And to any observer working with limited information, the system appears to have settled into one definite classical outcome. This is the modern resolution to a puzzle that Austrian physicist Erwin Schrödinger devised in 1935 specifically to highlight how absurd quantum superposition sounds when scaled up to everyday objects. In his famous thought experiment, a cat is sealed in a box alongside a radioactive atom that has a 50% chance of decaying within an hour, triggering a mechanism that would release poison, because the atom exists in a quantum superposition of decayed and not decayed until measured. Naive textbook logic seemed to suggest the cat itself should exist in a superposition of alive and dead, at least until someone opens the box to look. Schrödinger intended this as a criticism, a way of showing that something in the standard interpretation of quantum mechanics must be incomplete, because we never observe cats in such states. Decoherence theory, developed more fully by physicists including Wojciech Zurek starting in the 1970s and 80s, provided the missing piece. A cat is not an isolated quantum system. It is constantly entangling with an enormous number of surrounding particles, air molecules, photons, the material of the box itself. Far too many and far too quickly for any delicate quantum superposition to survive intact. Long before any human opens the lid, the cat has already effectively decided, through countless unavoidable entangling interactions with its environment, whether it is alive or dead. Zurek's related concept of Einstein, short for environmental-induced super, describes how only certain stable, resilient states, called pointer states, can survive this constant bombardment of entangling interactions, and it is these pointer states that end up looking like the solid, definite classical world we actually experience. The famous double-slit experiment, first performed with light by Thomas Young in 1801 and later repeated with individual particles like electrons, shows this same principle in miniature. When a particle's path is left undisturbed, it behaves like a wave, passing through both slits at once and interfering with itself. But the instant any detector, even a single stray photon, entangles with that particle to reveal which slit it passed through, the delicate interference pattern collapses, because the particle's which path information has now leaked out and become entangled with its surrounding. Exactly the same entangling process that governs the fate of Schrödinger's cat. just scaled down to the simplest possible system. Now here is where the arrow of time begins to emerge from this quantum fog. Imagine the universe just after the Big Bang, in its earliest moments. Matter and energy were compressed into an extraordinarily small volume, and crucially, in a state of remarkably low entanglement entropy relative to its later evolution. This is sometimes called the past hypothesis in physics. The idea that the early universe began in an extraordinarily special, low entropy configuration, even though it was hot, dense, and chaotic in a naive sense. From that starting point, as the universe expanded and particles interacted, entanglement inevitably spread. Particles that were once simple and independently describable became increasingly woven into one another's quantum states. Information that used to be locally accessible became smeared out across ever larger and more complex networks of entangled particles. This spreading of entanglement is, in a very real mathematical sense, irreversible in practice. Even though the underlying quantum equations remain perfectly reversible in principle. It is a bit like shuffling that deck of cards. Technically, you could shuffle a deck back into perfect order if you knew the exact sequence of every card movement and reversed it precisely. But in the real world, with billions of particles interacting in complex, chaotic ways, keeping track of every microscopic detail needed to reverse the process becomes so astronomically difficult that it might as well be impossible. For Neumann, entropy captures this same idea, but for quantum information. As entanglement spreads throughout the universe, the total amount of accessible, localized information shrinks, and the total amount of hidden, non-locally distributed information grows. What we experience, subjectively, as the passage of time may be intimately connected to this one-directional spreading of quantum entanglement. Some physicists working in the field known as quantum thermodynamics have proposed that the psychological and physical sensation of now moving toward later is fundamentally tied to this growth in entanglement entropy. As entanglement between a system and its environment increases, the system's history becomes progressively harder to reverse. And this asymmetry between an easy low-entropy past and an increasingly tangled, high-entropy future is what we perceive as time's arrow. This idea connects to something called the Page curve, first described by the physicist Don Page in the late 1990s while studying the puzzle of black hole evaporation. Page showed mathematically how the entanglement entropy of a system radiating information, like an evaporating black hole, should rise and then eventually fall as the system releases its information back out. This work, originally intended to help resolve the black hole information paradox, has become a central mathematical tool for physicists studying how entanglement entropy evolves over time in complex quantum systems generally, offering hints about how local pockets of order and disorder rise and fall even while total information is conserved. The black hole information paradox itself is worth pausing on, because it is one of the clearest places in all of physics where entanglement, entropy, and the arrow of time collide head-on. In 1972, the physicist Jacob Bekenstein proposed that black holes must carry entropy proportional to the surface area of their event horizon. A strange and counterintuitive idea at the time, since black holes were thought to be featureless objects with almost nothing describable about their interior. Stephen Hawking initially resisted this idea until his own calculations, published in 1974, showed that black holes are not perfectly black at all. Due to quantum effects near the event horizon, black holes slowly radiate particles. now called Hawking radiation, and consequently, they very gradually shrink and evaporate over unimaginably long timescales. This created an alarming problem. If a black hole eventually evaporates away completely, what happens to all the information about everything that ever fell into it? If that information is simply destroyed, it would violate the deep principle of unitarity that quantum mechanics depends on. The same principle that insists information can be hidden but never truly erased. For decades, this paradox divided the physics community, with some, including Hawking himself for many years, suspecting that information really might be lost inside black holes after all. Don Page's contribution was to show, mathematically, what an information-preserving evaporation process should actually look like from the perspective of entanglement entropy. If information is preserved, the entanglement entropy between the black hole and its escaping radiation should first rise, as the black hole and its radiation become increasingly entangled, and then, roughly at the halfway point of the evaporation process, it should turn around and begin to fall, as the correlations needed to reconstruct the original information gradually reappear encoded in the escaping radiation itself. This rise and fall is the Page curve, and confirming it, both through theoretical breakthroughs in the 2010s involving structures called quantum extremal surfaces, and through highly simplified analog experiments using quantum computers to simulate scrambling black hole-like systems, has become one of the most celebrated results in modern theoretical physics. It strongly supports the view that even black holes, the most extreme entropy generators in the universe, ultimately preserve information rather than destroying it, entangling it so thoroughly that it becomes practically, though never fundamentally, unrecoverably, echoing the exact same logic driving the everyday arrow of time all around us. This same body of work has deep connections to what physicists call the holographic principle, the startling idea, growing out of black hole thermodynamics and later formalized in specific mathematical models by physicist Juan Maldacena in 1997, that all of the information contained within a volume of space might, in principle, be fully encoded on that volume's boundary. Much like a hologram encodes a three-dimensional image on a flat two-dimensional surface, if space itself can be understood as emerging from entanglement patterns encoded on some boundary, then time, entropy, and even geometry may all be different faces of the same underlying entangled information. Network laboratories around the world have spent the past several years building increasingly precise tools to test these ideas directly, using platforms like trapped ions, superconducting qubits, and ultra-cold atoms, the same kinds of systems used in cutting-edge quantum computers. By carefully controlling small numbers of entangled particles, researchers can measure how quickly entanglement entropy grows as particles interact, and compare that growth against predictions from quantum thermodynamics. These experiments represent some of the most direct tests we have of the connection between entanglement, information loss, and the emergence of irreversible, one-directional behavior in otherwise reversible quantum systems. It is delicate, painstaking work, because entanglement is fragile, and the very act of trying to measure a quantum system risks destroying the fragile correlations you are trying to study. But as measurement techniques and quantum control have improved, these experiments have become steadily more precise, giving physicists an increasingly detailed, quantitative picture of how quickly information disperses, and how that dispersal relates to thermodynamic quantities like temperature and entropy that we can measure in the everyday, classical world. trapped ion systems, which hold individual charged atoms in place, using oscillating electric fields and manipulate them with finely tuned laser pulses, have become one of the most precise laboratories for this kind of work, because researchers can prepare a small handful of ions in a chosen entangled state and then track, almost particle by particle, exactly how correlations spread outward as the ions interact. Superconducting qubit systems, the same underlying technology used in many modern quantum computers, take a different approach, using tiny circuits cooled to temperatures colder than deep space, so close to absolute zero that thermal noise no longer overwhelms the delicate quantum behavior researchers are trying to observe. These circuits allow scientists to program specific interaction patterns between dozens or even hundreds of qubits and then measure how entanglement entropy grows across the resulting network, sometimes described as watching quantum information scramble across a system, spreading from a small local disturbance into a globally distributed pattern that becomes increasingly difficult to unwind. Ultra-cold atom experiments, which trap and cool clouds of atoms to temperatures near absolute zero using intersecting laser beams, offer yet another window, allowing researchers to simulate simplified many-body quantum systems and to directly image how entanglement entropy across different regions of the trapped cloud rises after the atoms are allowed to interact, providing some of the most direct experimental confirmations that entanglement entropy behaves quantitatively in close agreement with the mathematics of the second law of thermodynamics. Each of these platforms attacks the same underlying question from a different angle, and taken together, they represent one of the most active and fast-moving corners of experimental physics, precisely because a quantum computer, at its core, is essentially a carefully controlled machine for generating, manipulating, and measuring entanglement, which makes the tools built for quantum computing unexpectedly well suited to testing deep questions about the thermodynamic and temporal structure of reality itself. If this picture is correct, even in outline, it suggests something genuinely radical, that time is not a container the universe moves through, a kind of cosmic conveyor belt carrying events from past to future. Instead, time may be an emergent property, a statistical shadow cast by the relentless one-directional spreading of quantum information. The flow you feel, the sense that this moment is different from the last, and that neither can be undone, may not be a fundamental feature written into the bedrock of reality. It may be something closer to a macroscopic illusion, arising the same way that the smooth, continuous appearance of water arises from the chaotic motion of countless individual molecules, even though no single molecule has anything resembling wetness on its own. This idea has deep roots in a broader tradition within theoretical physics. The physicist Carlo Rovelli, known for his work on loop quantum gravity, has argued for years that time, in its most fundamental sense, might not exist at the deepest level of physical law at all. In his view, what we call the passage of time might be nothing more than the way thermodynamic and entropic processes appear from the limited, coarse-grained perspective of macroscopic observers like us, who can never track every microscopic detail of the universe around us. Whether or not every detail of this proposal is correct, it captures the same essential spirit as the entanglement-based picture, that time's arrow might be less about the universe fundamentally changing, and more about our own unavoidable ignorance of ever-spreading microscopic information. Working alongside mathematical physicist Alan Kohns, developed this idea further into what they called the thermal time hypothesis. Rather than assuming time exists as a fundamental backdrop and then asking how thermodynamic processes unfold within it, They explored the reverse possibility that the very notion of time, including its direction, might be derived entirely from the statistical, thermodynamic state of a system, essentially defining time as a mathematical byproduct of a system's entropy and the flow of correlations within it, rather than treating entropy as something that merely happens to change as time passes. This inverts the traditional relationship between time and thermodynamics so thoroughly that it forces a genuinely uncomfortable question. If time itself is derived from entropy and entanglement, then in a hypothetical system with no entropy gradient at all, would time exist in any meaningful sense whatsoever? This question echoes an older and famously unresolved puzzle in physics known as the problem of time, which emerges directly from attempts to combine quantum mechanics with general relativity. In the 1960s, physicists Bryce DeWitt and John Wheeler derived an equation, now called the Wheeler-DeWitt equation, intended to describe the quantum state of the entire universe, including gravity itself, all at once. The equation works mathematically, but it comes with an unsettling feature, unlike the ordinary Schrödinger equation, which describes how a quantum state changes over time. The Wheeler-DeWitt equation contains no explicit time variable at all. Taken at face value, it seems to describe a universe that simply does not change. A single frozen quantum state rather than an evolving one. Physicists have spent decades trying to understand how the vivid, undeniable experience of change and flow that we live through every day could possibly emerge from an equation that appears to describe a timeless universe. One influential proposal, put forward by physicist Julian Barber, embraces this timelessness directly, suggesting that the universe is best understood as an enormous collection of individual, timeless nows, each one a complete, self-contained configuration of everything that exists, with no true flow connecting one to the next. On this view, what we experience as motion and the passage of time is really just each timeless configuration containing embedded records, like memories and photographs, that create the illusion of a continuous, connected history, even though, fundamentally, each moment stands entirely alone. The entanglement entropy picture offers something of a middle path between these extremes, suggesting that while the deepest layer of physical law may indeed be timeless or symmetric, as Barber and the Wheeler-DeWitt equation both suggest, the steady, one-directional spreading of entanglement across a sufficiently large and complex system could be exactly the missing ingredient needed to stitch those timeless configurations together into the flowing, directional experience we actually have. It's worth being honest here about where the settled science ends and the frontier begins. The existence of entanglement and its role in decoherence is extraordinarily well established, confirmed across thousands of experiments and forming the working foundation of technologies like quantum computing and quantum cryptography. The mathematical relationship between von Neumann entropy and thermodynamic entropy in specific well-studied systems is also solid, rigorous physics. What remains more speculative and genuinely at the cutting edge of theoretical research is the precise claim that the psychological, subjective experience of time's passage is directly and quantitatively caused by this entanglement growth, rather than merely being correlated with it or emerging from some deeper, not yet fully understood layer of physics. Some researchers favor entanglement-based explanations. Others emphasize different aspects of statistical mechanics, or look toward ideas in quantum gravity where time itself may not be a fundamental variable at all. but something that only appears once you specify a physical system to measure change against. This is an active area of debate, not a settled conclusion, and any documentary claiming total certainty here would be overstating the case. What can be said with confidence is that entanglement entropy provides one of the most mathematically precise and experimentally grounded frameworks we currently have for connecting the reversible micro-world of quantum mechanics to the irreversible macro-world of lived experience. If entanglement really is the engine driving the arrow of time forward, then the implications reach far beyond the philosophical question of why we age. They touch on some of the biggest unresolved mysteries in modern cosmology. Consider what happens if entanglement continues spreading, unchecked, for an extraordinarily long time into the future. In an ever-expanding universe, matter grows more and more diffuse. Black holes slowly evaporate through a quantum process called Hawking radiation, discovered theoretically by Stephen Hawking in the 1970s. And eventually, according to many current cosmological models, the universe may approach a state of maximum entropy, sometimes called heat death. In this state, energy would be spread so evenly, and particles so thoroughly entangled with one another, that no meaningful gradients, no differences between hot and cold, no usable energy for any process, however small, would remain. Some physicists have speculated that in such a state, with entanglement entropy at its theoretical maximum and no further meaningful change possible, the very distinction between past and future might blur or even cease to have physical meaning. If time's arrow really does emerge from increasing entanglement, then a universe that can no longer increase its entanglement any further may, in some deep sense, stop experiencing time at all. Not because everything freezes, but because there would no longer be any directional asymmetry left to define a forward. There is an old and deeply strange mathematical theorem lurking behind this idea, called Poincare recurrence, named after the French mathematician Henri Poincare, who proved in the late 19th century that any closed physical system with a finite amount of energy will, given enough time, return arbitrarily close to any previous state it has occupied, including its earliest, lowest entropy state. In principle, this means that even a universe that has reached maximum entropy is not necessarily frozen forever. Given a length of time so vast it dwarfs any number normally used in science, far longer than the current age of the universe raised two enormous powers, a random fluctuation could, in theory, briefly reassemble a lower entropy configuration, and with it, however fleetingly, restart some local, small-scale flow of time. Most physicists treat this as a mathematical curiosity rather than a serious prediction about our actual universe, since our universe is not a simple, closed system bouncing around a fixed energy landscape. It is expanding, and by all current evidence, that expansion is accelerating, driven by whatever mysterious component of the cosmos physicists call dark energy, discovered through observations of distant supernova in the late 1990s by two independent research teams. Work that was recognized with the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. If this accelerating expansion continues indefinitely, as current data suggests it will, distant galaxies will eventually recede faster than light can cross the growing space between them, isolating every remaining pocket of matter into its own causally disconnected island, each one drifting toward its own private heat death, entangling internally until no further entanglement growth, and by extension no further meaningful flow of time, remains possible within it, it's worth returning for a moment to that strange starting condition we mentioned earlier, the extraordinarily low entropy state of the very early universe, because it remains one of the least understood ingredients in this entire picture. Physicist Roger Penrose has pointed out just how staggeringly improbable that initial low entropy condition appears to be, calculating odds so vanishingly small that ordinary numbers struggle to express them, essentially describing the improbability using a number with so many digits that writing them all out would be a practical impossibility. Why should the universe have begun in such an exquisitely unlikely, low entanglement, low entropy state in the first place, when the vast majority of possible starting configurations would have been high entropy from the very first instant? This remains one of the most significant open problems in cosmology. Some researchers look toward the theory of cosmic inflation, first proposed by physicist Alan Guth in 1980, which describes an extraordinarily rapid expansion of space in the first tiny fraction of a second after the Big Bang, as a possible mechanism for naturally producing such a smooth, low-entropy starting point. Others explore ideas from quantum cosmology suggesting that the low-entropy beginning might itself be explainable through the same entanglement mathematics used everywhere else in this story, perhaps arising from boundary conditions in a still undiscovered theory of quantum gravity. No consensus yet exists, and this gap, the unexplained origin of the universe's initial low entanglement condition, sits at the very foundation of the entire arrow of time problem. A reminder that even our best current mathematics describes how entropy grows far more successfully than it explains why it started so low to begin with. The tools available to attack this question keep expanding. Quantum computers, originally developed with entirely different goals in mind, like breaking cryptographic codes or simulating chemical reactions, have increasingly become unexpectedly powerful instruments for directly probing these foundational questions about entanglement, entropy, and time. Because a quantum computer's basic operation involves deliberately creating and manipulating large, controlled webs of entanglement between qubits, researchers can use these machines to simulate simplified toy models of scrambling systems designed to mimic, in miniature, how information disperses inside black holes or across large interacting quantum systems generally, then directly measure entanglement entropy growth in ways that would be effectively impossible using natural physical systems alone. This gives physicists something rare and valuable: a genuinely programmable laboratory for testing abstract mathematical predictions about entanglement, entropy, and information scrambling under carefully controlled, repeatable conditions. One of the more unexpected and genuinely exciting developments to emerge from the broader race to build increasingly capable quantum computing hardware. This connects to one of the grandest unanswered questions in physics: the search for a theory of everything, a single framework that could unify quantum mechanics, which governs the very small, with general relativity, which governs gravity, and the very large. One of the deepest tensions between these two theories is precisely about time. In quantum mechanics, time is typically treated as a fixed background parameter, a kind of universal clock against which everything else changes. In general relativity, by contrast, time is flexible, woven together with space itself into a single four-dimensional fabric that can stretch, warp, and even, near a black hole's singularity, break down entirely. Any successful unification of these two frameworks will likely need to explain not just how gravity behaves at the quantum level, but what time actually is at the most fundamental level. And growing entanglement entropy is one of the leading candidates physicists are exploring for how a directional, flowing sense of time could emerge from a deeper theory where it might not exist as a fundamental ingredient at all. There is something quietly humbling in all of this. For most of human history, time felt like the most solid, unquestionable feature of reality there could possibly be. Clocks tick. Seasons pass. We are born, we grow, and eventually we are gone. It seemed almost absurd to ask whether time itself was real in any deeper sense, the way you might ask whether a particular color or sound was real. And yet, when physicists trace the mathematics all the way down, past the level of clocks and calendars, past even the level of atoms and heat, down into the strange, correlated web of quantum entanglement connecting every particle in the observable universe, the sturdy, one-directional river of time that we take for granted starts to look less like bedrock and more like the visible surface of something deeper and stranger, a slow, silent draining of information out of view, one entangled particle at a time. What we still do not know may be even more interesting than what we have already learned. We do not yet have a complete, universally agreed upon theory, connecting entanglement, entropy, to every aspect of thermodynamic and psychological time. We do not fully understand how, or even whether, consciousness itself plays any special role in how time is perceived, beyond simply being another physical system subject to the same entropic processes as everything else. We do not know for certain what happens to the concept of time in the earliest fractions of a second after the Big Bang, when quantum gravitational effects, not yet captured by any complete theory, may have dominated. And we do not know whether the approach to maximum entropy in the far future truly represents an end to time's flow, or merely a transformation into some form we do not yet have the mathematics to describe. There is a deeply personal dimension to all of this, one that reaches beyond distant black holes and cosmological endgames and into the texture of ordinary experience. Why do you remember yesterday but not tomorrow? Why does a broken vase never spontaneously reassemble itself in your memory of the future the way it stubbornly refuses to in the physical world? The physicist and cosmologist Sean Carroll has argued that memory itself is fundamentally a thermodynamic process, deeply tied to the same entropy gradient driving every other arrow of time in the universe. Forming a memory means creating a physical record, a pattern of neural connections, chemical changes, or, in principle, any physical structure at all that correlates with a past event. Creating that correlated record necessarily increases the entropy of the surrounding environment. In the same way that writing information onto any physical medium requires energy and generates heat. Echoing directly back to Landauer's principle about the thermodynamic cost of information. Because entropy only reliably increases in the same direction that we call forward. Reliable memories can only ever form about the lower entropy past, never about the higher entropy future. This gives us, without any special biological or psychological ingredient beyond the ordinary laws of physics, a built-in reason why every conscious mind that has ever existed experiences time flowing in exactly the same direction as the thermodynamic arrow, and never the reverse. This insight also offers a resolution to Boltzmann's old, uncomfortable worry about spontaneous fluctuations, the unsettling possibility that a random, low-probability quantum or thermal fluctuation could momentarily assemble something resembling a conscious brain, complete with false memories of an entire life never actually lived, drifting alone in an otherwise featureless, maximum entropy universe. Physicists call this hypothetical entity a Boltzmann brain, and if such spontaneous fluctuations really were the dominant source of conscious observers in an eternal or near-eternal universe, then simple statistics would suggest we should expect to be isolated. Momentary brains rather than embedded observers within a vast, structured, historically consistent cosmos. Most cosmologists treat the overwhelming prevalence of ordinary, structured observers like ourselves, embedded in a consistent history with reliable memories and an ordered surrounding universe, as strong evidence against models that would predict Boltzmann brains as common, and it remains one of the sharpest tools cosmologists use to rule out otherwise mathematically plausible models of the universe's long-term future, precisely because those models fail the basic test of predicting that beings like us, with rich, connected memories embedded in a coherent history, should be common rather than statistically vanishingly rare. None of this is settled beyond all debate. The relationship between conscious experience and the physical arrow of time remains one of the most contested intersections of physics and philosophy, and reasonable researchers disagree about exactly how much of subjective experience can be explained through entropy and information alone, versus how much may require ideas from neuroscience, philosophy of mind, or physics not yet discovered. But the striking part, the part that keeps drawing serious physicists back to this question again and again, is how much explanatory weight a single, well-defined physical quantity, the steady, one-directional growth of entanglement entropy, appears able to carry, connecting the coldest, most abstract mathematics of quantum information theory all the way to the warm, deeply familiar feeling of remembering yesterday and wondering about tomorrow. What keeps researchers pursuing this question across quantum information theory, cosmology, and the foundations of physics is the recognition that time is not just one topic among many. It touches everything, every measurement, every experiment, every observation in the history of science has been made by beings embedded within the flow of time, using clocks and memories that are themselves products of entropy's steady increase. To understand where that flow comes from is, in a very real sense, to understand something about the deepest scaffolding underlying all of physical law, and perhaps about the strange, quiet nature of existence itself. Not a story unfolding within time, but time itself unfolding, one small, hidden piece of quantum information at a time.